Chapter 6 is about exponential and logarithmic functions. In this chapter, we are going to go over 6.1 through 6.6. Six point one is exponential functions. 6.2, we are going to learn about the graphs of exponential functions. And in 6.3, the logarithmic functions. 6.4, graphs of logarithmic functions. 6.5, logarithmic properties. And 6.6, exponential and logarithmic equations. Six point one, exponential functions. In this section, you will learn how to evaluate exponential functions, how to find the equation of an exponential function, and how to use compound interest formula and evaluate exponential functions with base e, the natural base. A function is called an exponential function if it is expressed in the form a times b raised to power x, where a is a non-zero real number called the initial value. This is the value when x equals to 0. B is a positive real number, which is different from 1. If b equals to 1, then we have a constant function, but b must be positive. The domain of f is all real numbers, and the range is all real numbers if a is positive, all positive numbers if a is positive, and all negative numbers if a is negative. So a is what determines the range of f. The y-intercept is the point 0a, because when x equals to 0, f of 0 equals to a, and the horizontal asymptote is at y equals to 0, because if x tends to minus infinity, then y will be 0. Which of the following equation is an exponential function? We can look at the first equation, which can be expressed as 4, 3x minus 2. And we can rewrite it as 4 raised to power 3 times x times 4 raised to power minus 6. So it can be expressed as a number times a number raised to power x, which is an exponential function. So actually the only function here which is not an exponential function is g of x equals to x cubed. Another function which is not exponential function is j of x equals to minus 2 raised to power x. So there are two functions here that are not exponential functions. The first one is the polynomial g of x equal to x cubed, and the second one is j of x equals to minus 2 raised to power x. It's not an exponential function because b, which is minus 2, is negative. Consider the function f of x equals to 5 times 3 raised to power x plus 1. Let's correct this one. So evaluate f of 2 without using a calculator. The solution, we follow the order of the operation to change f of x to 5 times 3 raised to power x plus 1, which is actually f of 2 is 5 times 3 raised to power 2 plus 1, which is 5 times 3 raised to power 3 equals to 5 times 27 equals to 135. And the application of the exponential function is the exponential growth. So if we are given two data points, we can be able to write an exponential model using the 2 points. If one of the points has the form 0a, that is the initial value, then we can use it and substitute the second point into the equation f of x equal to a b raised to power x and solve for b. The second, if neither of the data point have the form 0a, then we substitute both points into the equation to get two equations that we will solve for a and b. So using the a and b found in the steps above, we can write the exponential function. As an example, in 2006, 80 deer were introduced into a wildlife refuge. By 2012, the population had grown to 180 deer. The population was growing exponentially. Write an algebraic function n of t representing the population n of deer over time t. So to solve this problem, we are going to realize first that 2006 is the initial time when t equals to 0. So we have the initial value, t equals to 0, and the population is 80. So we have 0, 80. And then we can observe that from 2006 to 2012, there are 6 years. So 6 years later, the population has grown to 180, which provides us with the second point. Given that this equation is an exponential function, we are going to consider a as 80 from the initial value, and our formula for the exponential function is n of t equals to 80 times b raised to power t. To find b, we will replace the point 6, 180 into the equation to have 180 equals to 80 b raised to power 6. Solving this equation will give us that b is the city root of 9 over 6. That is the city root of 3 over 2, which is 1.1447. So the formula for the growth of the population of deer at time t is 80 times 1.1447 raised to power t. Another example, writing an exponential model when the initial value is not known. In this case, the initial value is not known. We want to find an exponential function that passes through the point -2, 6 and 2, 1. So we will fit both points into the equation. So for the point -2, 6, we will have 6 equals to a times b raised to power -2. And for the point 2, 1, we will have 1 equals to a b squared because x is 2. So use the first equation to solve for a in terms of b. So we have that a equals to b, a equals to 6 times b squared. So we are going to replace a in the next slide. So a equals to 6b squared. Now from the second point, 1 will be equal to a times b squared. So we have that 1 equals to 6b squared times b squared, which is 6 times b, 4. So b equals to the fourth root of 1 over 6. Using a calculator, you will get that b equals to 0.6389. So use the value of b in the first equation to solve for the value of a. Recall that a equals to 6b squared, so we replace b by its value and square it. We will square it and to have a equals to 2.4492. So the equation of this exponential function is now f of x equals to 2.4492 times 0.6389 raised to power x. Sometimes we will be given a graph of an exponential function, and we would like to determine that function, it will be smart to first identify the intercept, the y-intercept 0a, identify the point 0a, and then any other point of the graph, and use those two as points that can be used as we did on the previous slide to find the equation of the exponential function. You can follow these first steps, these 4 steps. First, identify 2 points, which could be the y-intercept and any other point. Then use the y-intercept to get an equation, and the second point to get the second equation. So, compound interest formula. The compound interest is another example of exponential, of application of an exponential function. So the corresponding interest can be calculated using the formula A of t equals to P times 1 plus R over N raised to the power N t, where A of t is the account value, the value in the account, T is measured in years, P is the starting amount of the account, the initial amount, also called the principal, or more generally, the present value, how much money you have deposited into your account. R is the annual percentage rate expressed as a decimal, and N is the number of compounding period in 1 year. How often are they going to compute the interest and add to the actual value? Example, calculating compound interests. If we invest $3,000 in an investment account, given paying 3% interest compounded quarterly, how much will the account be worth in 10 years? So here the initial value is 3,000. The interest rate is 3%. We will express R as 0.03. Because the compounding is quarterly, we will assume that the number of times the interest will be compounded will be 4, so N equals to 4. So we want to know the value of the account 10 years later. So we are looking for A of 10. So the formula here will have T equals to 10, and A of 10 will be 3,000 for P, times 1 plus 0.03 over 4, raised to power NT, which is 4 times 10. Using your calculator, 10 years later, the amount of money in the account will be 4,045.05. So the account will be worth $4,045 in 10 years. The number E. The number E, also known as the natural base of the exponential function, is the limit of the expression 1 plus 1 over n raised to power n as n tends to infinity. You can always check this by doing some computation with your calculator. Take n equals to 1, you will have 1 plus 1 raised to power 1, which is 2. Then n equals to 2, you will have 1 plus 1 over square, and so on. So the value of E is approximately 2.718282. So the constant value was named by the Swiss mathematician Leonhard Euler. Euler, that's where we get the letter E, who was born in 1707 and died in 1783. He's the first to investigate and discover many of the properties of the natural logarithm and the natural exponential. So sometimes we may want to compound interest to compute the amount available at a continuous interest. That is, the interest is compounded continuously. The formula for this is A of t equals to A e raised to power RT, where R is the interest rate and T is the time. So R is positive, so the formula represents a formula of an exponential function. So we can re-express this as a of t equals to p raised to power e raised to power rt, where p is the initial amount invested, r is the growth rate or the interest rate per unit time, and t is the period or term of the investment. So we can use the continuous growth and decay formula depending on what the value of R is. So given the initial value, the rate of growth or decay and time t, solve a continuous growth or decay function. To do this, you will use the information in the problem to determine the initial value A or P, and then use the information in the problem to determine the growth rate R. If the problem refers to continuous growth, then R is positive. If the problem refers to a continuous decay, then R is negative. So we can use the information in the problem to determine the time t. Substitute the given information into the continuous growth formula and solve for A of t. Example for continuous growth. A person invests $1,000 in the account earning a nominal 10% per year, compounded continuously. How much was in the account at the end of 1 year? The solution. Since the account is growing in value, this is a continuous compounding problem with a rate R equals to 0.1 for 10%. The initial investment was 1,000, so P equals to 1,000. We use the continuous compounding formula to find the rate after 1 year. So A of t equals to PERT, which is 1,000. T equals to 1, so R is 0.1. Using a calculator, we will get 1,105.17. Now calculating continuous decay. Radon 222 decays at a continuous rate of 17.3% per day. How much will 100 milligram of radon 222 decay to in 3 days? Solution. Remember, we need an initial value. The rate here is 17.3%, which is negative because it is decaying, it is reducing. So R equals to negative 0.173. The initial amount of radon 222 was 100 milligrams, so A equals to 100. So we can use the continuous decay formula to find a value after t equals to 3 days. So A of t equals to A times ERT, which is 100, E raised to power minus 0.173 times 3. So the quantity remaining will be 59.5115. We can use a calculator to compute this. So 59.5115 milligram of radon 222 will remain after 3 days. In each of these problems, we want to pay attention from the information that we have to know what is the rate either of growth or decay, and any other information we may be given in the problem to determine the second point, which is useful in defining the growth or the exponential function formula. Graph of an exponential function. In this section, we will learn how to graph exponential function and how to transform some of those graphs. So an exponential function with the form f of x equal to b raised to power x, where b is positive, b is different from 1, has 3 characteristics. It is a one-to-one function. The horizontal asymptote is y equals to 0. The domain is the whole real line, all the real numbers. The range is 0 to infinity. There's no x-intercept. The y-intercept is 0, 1. That is when x equals to 0, y equals to 1. It's an increasing function because b is greater than 1. is increasing when b is greater than 1, and it is decreasing when b is less than 1. These are the characteristics of an exponential function of the form b raised to power x. Now, these are two graphs representing exponential function. The first one is the graph for b raised to power x when b is greater than 1. It is an increasing function. The second one is the graph for the same type of function, but b is between 0 and 1, and we have a graph of a decreasing function. So given an exponential function of the form f of x equals to b raised to power x, we can graph the function by creating a table of points. Usually 2 or 3 points are useful. We plot at least 3 points from the table, including the y-intercept 0, 1. Draw a smooth curve through those points. State the domain, negative infinity to infinity, and the range is from 0 to infinity. There is a horizontal asymptote at y equal to 0, that is, the x-axis is a horizontal asymptote. The graph is not supposed to cross the x-axis. This is an example of the graph of f of x equal to 0.25. First, we will identify here that b is a number between 0 and 5. So we have an idea of the shape of the graph from left up to right down, but not crossing the x-axis. So we have some points here, -3, we will have 64. 0, we have 1. When x equals to 0.25, when x equals to 1, we have y equals to 0.25, and so on. We plot this point into the graph to the right of the screen, and we just draw a smooth curve passing through those 3 points. We can obtain any other exponential function by transforming the graph of the basic function f of x equal to bx. So we will call a vertically, for any constant c and d, the function f of x equals to b raised to power x plus c plus d, shift to the parent function f of x equal to b raised to power x, vertically d unit in the same direction of the sign of d, horizontally c unit in the opposite direction of the sign of c. Remember what we did in shifting functions. And the y-intercept becomes 0, bc plus d. The horizontal asymptote is d. The horizontal asymptote is y equals to d. The range becomes d to infinity, and the domain is -infinity to infinity. It remains unchanged, the domain. So, to draw the graph, we will first draw the horizontal asymptote y equals to d, and then identify the shift from -c to d as -c to d. Shift the graph of f of x left c unit if c is positive, and right unit if c is negative. And shift the graph of b of x up d unit if d is positive, and down d unit if d is negative. Then we state the domain and the range. So this is an example. Graph the function f of x equals to 2 raised to power x plus 1 minus 3. Here we can observe that b is 2, so it's an increasing graph. Now, d is -3, so we will have a horizontal asymptote at y equals to -3. The original graph of f of x equals to 2x will be shifted below up to 3, -3. And then we are going to shift we will shift the y-intercept to the right at the level of 1, 1, 0. So identify the shift at -cd. So the shift is -1, -3. Shift the graph f of s bx left 1 unit and draw 3 units and down 3 units. So we get the graph that you can see here. So it is this graph of f of x equals to 2 raised to power x. Shift left, shift down by 3 units and left by 1 unit. We can also stretch and compress the parent function f of x, that is multiplying it by a, is a stretch vertically by a factor a if absolute value of a is greater than 1, compress vertically by a factor of a if absolute value of a is less than 1. This is exactly what we did in the previous chapters about function, how we transform functions. So the y-intercept of it has a y-intercept 0a and has a horizontal asymptote at y equals to 0, a range 0 infinity, and a domain from -infinity to infinity. This takes us back to the regular exponential function. So what we are saying so far is that every exponential function could be obtained from the basic exponential function b raised to power x. So this is an example of a graph f of x equal to 4, half x. Here, b is half, that means we will have a decreasing function. Since a equals to 4, the graph of f of x, half x, will be stretched by a factor of 4. So we can plot the y-intercept, which is 0, 4, along with two other points. We can use -1 infinity, -1, 8, and 1, 2, and then sketch our graph. We can also do a transformation by a reflection. So find the graph of the equation of the function g of x that reflect f of x, a quarter raised to power x about the x-axis. State its domain, range, and asymptote. So if we have our function f of x equals to 1/4 raised to power x, that's what we have here. We can multiply f of x by -1 to get g of x equals to -1/4 raised to power x. That's what we call a reflection of f of x about the x-axis. So we are just going to reflect the graph of 1/4 x, which we know how to get with respect to the x-axis. That's the graph you see to the right side of the screen. Is the graph of a quarter raised to power x reflected about the x-axis. So most general transformation of exponential functions. So combining what we have done so far, we will say that a translation of an exponential function is in the form f of x equal to a, bx plus c plus d, where the parent function y equals to bx with b greater than 1 is shifted horizontally, c unit to the left, stretched vertically by a factor of absolute value of a if absolute value of a is positive, and compressed vertically by a factor of a if absolute value of A is between 0 and 1. Here is if absolute value of A is greater than 1. So graphing reflection, we have discussed this. So the function f of x equals to negative b raised to power x reflect the parent function f of x equals to bx about the y-axis. I've skipped the first two lines because that's what we covered in the previous section. So in the previous example, so we can have the function f of x equals to minus b raised to power x, reflect the parent function about the x-axis, has a y-intercept 0, -1, and has a range from -infinity to 0. Has a horizontal asymptote at y equals to 0, and the domain is -infinity to infinity. So f of x equals to b raised to power minus x, reflect the parent function f of x equals to b raised to power x about the y-axis, and has a y-intercept at 0, 1, a horizontal asymptote at y equals to 0, and a range from 0 to infinity, and a domain of all real numbers, which are unchanged from the parent function. 6.3, logarithmic function. We are going to learn how the logarithmic function is connected to the exponential function and vice versa. We learn to evaluate logarithmic function and look at some common properties of logarithm. We'll also learn about the natural logarithm. What is a logarithmic function? A logarithmic function is a function y equals to logarithm of bx whenever x equals to b raised to power y, so is the inverse function of an exponential function. So we remember we define an exponential function as y equals to b raised to power x. Now, if x equals to b raised to power y, so y is the logarithm of x. That's essentially what the logarithm is about. So the domain of a logarithm function is all positive real numbers. That is all numbers that are greater than 0. And the range is every real number. Remember, for exponential function, the domain was every real number and the range was positive numbers. The inverse of the exponential function is called the logarithmic function, and the domain is the range of the exponential function. The domain is the range of the exponential function, and the range is the domain of the exponential function. So write the following logarithmic equation in exponential form. The first one is logarithm of square root of 6 to base 6 equals to half. And then logarithm of 9 in base 3 equals to 2. So when we say logarithm of square root of 6 in base 6 equals to half, it means that the square root of 6 is 6 raised to power half. That's essentially what it means. So let's look at the solution. Using the basic definition of logarithm, we say that y equals to logarithm of x in base b if x equals to b raised to power y. So in the first equation, logarithm of square root of 6 in base 6 equals to half, where b equals to 6 and y equals to half, means that x is 6 raised to power half, which is square root of 6. Therefore, the equation is equivalent to square root of 6 equals to 6 raised to power half. Now, logarithm base 3 of 9 equals to 2 means that 3 raised to power 2 equals to 9. These are just a way for you to understand the meaning of logarithm. The logarithm is just a way to describe the power of a number with respect to another number. That other number is the base. Let's look at the logarithmic function with exponential. If we say 2 raised to power 3 equals to 8, then logarithm of base 2 of 8 is 3. That is, 8 is the power of 2. I'm sorry, 3 is the power of 2 that will make 8. So when we say 5 squared equals to 25, logarithm of 25 is the power of 5 that will give 25, and then we get 2. When we say 10 raised to power minus 4 equals to 1 over 10,000, we will want to know what is the power of 10 that will give 1 over 1,000, and we will get minus 4. That is the question we answer when we are looking for the logarithm. Of course, in most cases, you will need your calculator when we don't have a perfect square or numbers that you can easily identify what power it is. Example, solve the equation y equals to logarithm in base 4 of 64. In other words, what is the power of 4 that will give 64? So we know that 4 cubed equals to 64. So logarithm in base 4 of 64 is 3. Second equation, what is the power of 3 that will give 1 over 27? Here we are dealing with a decimal number. We will observe that we want to find y so that 3 raised to power y is equal to 1 over 27, which is 1 over 27 is 3 raised to power 3, so 1 over 27 is 1 over 3 raised to power 3, which is 3 raised to power negative 3. So 1 over 27 is 3 raised to power negative 3. The power of 3 that will give 1 over 27 is negative 3. So the logarithm in base 3 of 1 over 27 is negative 3. So logarithm is just a way to reverse the powers, the exponential. A common logarithm is the logarithm with base 10. It is usually called the common logarithm. So when the base is 10, like powers of 10, we call it the common logarithm. So for example, what is the logarithm of 1,000 in base 10? We will instead say, what is the common logarithm of 1,000? In other words, what is the power of 10 that will give 1,000? And the answer will be 3. If I ask, what is the logarithm in base 10 of 1 million? That is, what is the common logarithm of 1 million? We will be looking at what power of 10 will give 1 million, and we will have 6. So in this example, we are looking at how to rewrite and solve a real-world problem exponential model. Example, the amount of energy released from one earthquake was 500 times greater than the amount of energy released from another one. This is an expression. The equation 10 raised to power x equals to 500 represents this situation. It is known that way, where x is the different magnitudes on the Richter scale to the nearest 1,000. What was the difference in magnitude? So we begin by rewriting the exponential equation in logarithmic form. So if somebody tells us that 10 raised to power x equals to 500, that means the power of 10 that will give 500 is x. In other words, what is the common logarithm of 500? We can use a calculator to determine the common logarithm of 500, and that gives us the solution to this equation. Another type of logarithm which is commonly used is the natural logarithm. Remember from the natural exponential e, the natural logarithm is the inverse of the natural exponential function, and it is denoted by ln, natural logarithm. Sometimes people use capital L. So when we write y equals to ln of x, it is equivalent to e to the y equals to x. So the domain of the natural logarithm, like the domain of a logarithm in general, is all positive numbers, and the range is all real numbers. So as we learn for all functions, and in particular for the exponential function, we can also make a logarithmic shift of a function. So consider the function f of x equals to logarithm in base 2 of x plus 3. What is the domain? We will recall that the domain of a logarithmic function is all positive numbers. So logarithm base 2 of x plus 3 is valid if x plus 3 is positive. That will mean x is greater than negative 3. And the domain of this shift function becomes negative 3 to infinity. Same thing if we have a function f of x equal to logarithm of 5 minus 2x. To find the domain, we will recall that the logarithm is only defined for positive function. So in this case, we will set the condition that 5 minus 2x is positive. That means x is less than 5 over 2. And the domain is from negative infinity to 5 over 2. To graph a logarithmic function, we will draw and label the vertical asymptote x equals to 0, plot the x-intercept 1, 0, plot the key point b1, and draw a smooth curve through the points. Remember that the logarithmic function is just the inverse of an exponential function. So in other words, using the property of graph of an inverse, we can always obtain the graph of the exponential, picturing the graph of the logarithmic function, picturing the graph of an exponential function. So look at the two graphs here. We have the graph in base b. When b is greater than 1, remember for the exponential, we divided cases where b is greater than 1 and the case when b is between 0 and 1. So we will obtain the graph of a general logarithmic function as an increasing function when b is greater than 1 and a decreasing function when b is between 0 and 1. In both cases, an x-intercept, that is the point where y equals to 0, x equals to 1. So to graph the function logarithm of x in base 5, for example, let me correct this. We will state the domain, the range, and the asymptote. Before graphing, identify the behavior and key point for the graph. For the behavior, b equal to 5 is greater than 1, so we know that the function is an increasing function. The left tail of the graph will approach the vertical asymptote x equal to 0, and the right tail will increase slowly without bound. So the x-intercept is 1, 0, and the key point we have is 5, 1, is on the graph. We draw and label the asymptote, plot and label the point, and draw a smooth curve through the point. So this is the graph of the logarithmic function with base 5. So identify the two key points, the x-intercept 1, 0, and the point when x equals to 1. When x equals to 5, I'm sorry, b equals to 1. When x is the base, the logarithm is 1. We can also perform horizontal shift of a logarithmic function. For any constancy, the function f of x equals to logarithm in base b of x plus c, if we consider it as a base function, do this corrections. We have to change and write it as a base. So this is logarithm in base b of x. So for any constant c, the function f of x equals to logarithm in base b of x plus c. We shift the parent function y equals to logarithm in base b of x left by c unit. Remember, we have plus c here. Let's put this in brackets so that you observe that it is actually all under the logarithm. They shift the parent function to the right if c is negative. We have always been doing that. Right? C is negative. And has a vertical asymptote at x equals to minus c, and has a domain minus c to infinity, and has a range minus infinity to infinity. And so these are the graph. The original function is in blue here, logarithm in base b of x, and the shift to the left or right of x plus c is here in red. 6.5, the properties of the logarithmic function. The logarithmic function, like the exponential function, have some interesting properties for product, quotient, power, or that we are going to review in section 6.5. Product. The logarithm of the product is the sum of the logarithm. That is, the logarithm of m times n is logarithm of m plus logarithm of n. And the logarithm of m over n is logarithm of m minus logarithm of n. So this logarithm separate products and quotient into addition and subtraction. Example here, let's consider the value z equals to logarithm in base 3 of 64 over 3. So logarithm base 3 of 64 over 3 will be logarithm base 3 of 64 minus logarithm base 3 of 3. And naturally, we will observe that the logarithm of 3 base 3 is 1. Okay, this is a little disturbing. So here we will do logarithm of 64 in base 3 is logarithm of 4 times 16. And logarithm of 3 in base 3 is 1. So this becomes logarithm of 4 plus logarithm in base 3 of 16 minus 1. Logarithm, which is logarithm of 4 in base 3 plus logarithm of 4 times 4 in base 3 minus 1. We will continue to split 4 times 4 into logarithm of 4 plus logarithm of 4 plus logarithm of 4 minus 1, which give us logarithm of 4 base 3 times 3 minus 1. So z is 3 logarithm of 4 in base 3 minus 1. We apply both the, we have applied here both the product and quotient rules. So the power rule of a logarithm can be used to simplify the logarithm of a power by rewriting it as a product of the exponent times the logarithm of the base. Actually, the power of the logarithm formula is just the same as the multiplication or the product rule. For example, if we have logarithm of m raised to power n in base b, we can as well say it's logarithm of m multiplied by itself n times. So the logarithm is going to transform that multiplication into a sum, and it will become n logarithm in base b of m. For example, y equals to logarithm of 27 base 3 can be rewritten as logarithm of 3 raised to power 3, which is equal to 3 logarithm of 3. And logarithm of 3 in base 3 is 1, so it's equal to 3, which is just the definition of the logarithm. Logarithm in base 3 of 9 over 2 is logarithm of 9 in base 3 minus logarithm of 2 in base 3, which is logarithm of 3 square minus logarithm of 2 base 3, which is 2 minus 3 minus logarithm of 2 in base 3. And more example, rewrite the expression natural logarithm of x4y over 7. To write this expression, we first use the quotient rule, separating the quotient. It will be logarithm of x4y minus logarithm of 7. Then use the product rule, separating the product, logarithm of x4 plus logarithm of y minus logarithm of 7. So sometimes in some complex expression, you want to remember the rule of separation of logarithms. So we can express the logarithm at a base into another logarithm with another base. For example, if we have logarithm b of base m, we can change it into logarithm of m in base n divided by logarithm of b in base n. The base could be 10, or the base could be 3 or 2. N could be any of those numbers. So we can use it also to do the change of base from a base b to the natural logarithm, or a base b to the common logarithm in base 10. Section 6.6. Logarithm, exponential, and logarithm equations. So we are going to learn in this section how to solve exponential equation by applying logarithm of logarithmic equations by applying exponential equations, essentially. So the basic rule is that to solve an exponential equation, you apply the inverse of an exponential, which is the logarithm. And to solve a logarithmic equation, you apply the exponential equation as the inverse. So for example, if we want to solve the exponential equation 2 raised to the power x minus 1 equals to 2 raised to the power 2x minus 4, we may just apply the logarithm of both sides, and we will have x minus 1 equals to 2x minus 4. Solving, we will get x equals to 3. Here we have an equation which seems to be not to be from the same base. We have 8 raised to the power x plus 2 and 16 raised to the power x plus 1. We can easily identify that we can transform them into a common base, which could be base 2. So 8 is 2 raised to the power 3, and 16 is 2 raised to the power 4. Rewriting the equation with the new base of 2, we will have that it becomes 2 raised to the power 3x plus 6 equals to 2 raised to the power 4x plus 4. Solving, we have x equals to 2. So sometimes an exponential equation will not have the same base. And in this case, taking a common base like the natural logarithm or the common logarithm will help us to solve the problem. So if one of the terms in the equation is in base 10, for example, transform the other one in base 10. So make sure that all the terms becomes in the same base. Example, 5 raised to power x plus 2 equals to 4 raised to power x. We may just apply the natural logarithm to both sides and then maintain the logarithm to solve the equation as we did in this example. If we are asked to solve the equation y equals to a e to the kt, for example, solve 100 equals to 20 e to the 2t for t. So we will solve this equation using the natural logarithm because there is e there, is a natural logarithm base, and we will find t equals to logarithm of 5 over 2. Suppose we have an equation like e2x minus ex equals to 56. So we will observe that this equation looks like a quadratic equation because the unknown terms of the first, the unknown term is e to the 2x minus e to the x. It looks like e to the x squared minus e to the x. So I will set capital X equal to e to the x to transform this equation into a quadratic equation, observing that factors of minus 56 could be 7 and minus 8, and the sum of 7 and minus 8 give us minus 1. That quickly helped me to get two solutions. One is minus 7 and the other one is 8. Because the exponential cannot be negative, I will get rid of minus 7 and only solve the exponential equation e of x equals to 8. If e of x equals to 8, then x equals to natural logarithm of 8. So we will write here so x here is the natural logarithm. So we do the same if we have a logarithmic equation at a certain base. We apply the exponential function at the inverse of the logarithm. Example, we are asked to solve the equation natural logarithm of x squared equals to natural logarithm of 2x plus 3. So because the natural logarithm is a one-to-one function, we apply the inverse of it, which is the natural exponential, and it gives us x squared equals to 2x plus 3. So our equation is now x squared minus 2x minus 3 equals to 0. And the solution to this is minus 1, 3. You can observe that if you multiply 1 by minus 3, you get minus 2. So taking the factorization rule, we have x equals to minus 1 or x equals to 3, which are both solution. When we replace into the equation, always replace your solutions into the original equation to see that no rules has been violated. (6.7) The exponential and logarithmic model. So in this section, we will learn how to model exponential growth and decay, use the Newton's law of cooling, and use the logistic growth model. Choose an appropriate model for data. Express an exponential model in base 8. So modeling exponential growth and decay, we have here the graph of an exponential growth and exponential decay as we learned before. And here is the graph of the function a0 e to the kt, where a0 is the initial value. Example, a population of bacteria double every hour. If the culture started with 10 bacteria graph the population of a function of time, as a function of time. So when an amount grows at a fixed percent per unit time, the growth is exponential. To find A0, we use the fact that A0 is the amount at time 0. So A0 is 10. To find K, use the fact that after 1 hour, the population doubles from 10 to 20. That gives you the second point. So we fit this into the equation, 20 equals to 10 raised to power ek. So K equals to logarithm of 2. So the exponential function describing this population is y equals to 10 e to the logarithm of 2t, which we will separate using logarithm of ln, exponential ln2 is 2. So the final equation is y equals to 10 times 2 raised to power t. Using the product rule for exponential, the power rules for exponential. So one of the common terms associated with exponential decay, as stated above, is the half-life. The length of time, the half-life is the length of time it takes an exponentially decaying quantity to decrease by half of its original amount. So if you know the half-life of a radioactive isotope, for example, you will be able to find the value of K. So to find the half-life of a function describing exponential decay, solve the following equation. Half of A0 equal to A0 e to the kt. If you know K, then you will be able to get A0. If you know A0, you will be able to get K. For example, the half-life of carbon-14 is known to be 5,730. This is always known. Express the amount of carbon-14 remaining in as a function of time t. So as a function of time t, we know that A equals to, let's call it A of t. A is the amount at time t, A0 e to the kt. So using the half-time formula, we can find the value of K by solving the equation. Half of A0 will occur when t equal to 5,730. Fitting it into the equation, we have to solve logarithm of half equals to 5730K. So K equals to logarithm of half divided by 5730. So the equation of the quantity of carbon-14 remaining is A equals to A0, the initial quantity, e to the logarithm of half over 5730 t. So this equation is going to be used each time you have a problem of carbon-14. So we can compute the quantity logarithm of half over 5730, K, which is minus 1.2097, 10 raised to power minus 4. Is a negative function, is a negative value describing an exponential decay. Example. Finding the age of a bone. Let me put this example on the slide. A bone fragment is found that contain, a bone fragment is found that contains 20% of its original carbon-14. To the nearest year, how old is the bone? So we will say that if the original quantity was A, then what is remaining now is 0.8 times A. So if we know the quantity remaining, we can solve for T to know how old was the bone. So this is actually solving the equation for T. K is already given, as I told you, for each problem involving carbon-14, K is given as negative 1.2 We have the value of K here, negative 1.2097. So actually, in this problem, we are solving the equation A0. We can rewrite it here. This is our K. Remember, we had, actually, we are solving the equation point. We are solving the equation of what is a bone fragment is found that contain 0.2. So what is left is 0.2. So we are solving the equation 0.2 times A is equal to, let me write that equation here because it is missing. So 0.2 times A, that is what is remaining, 20%, is equal to A0 times. Now we are going to replace this by negative 1.2. I would have written it as negative 1.20 raised to power 10 raised to power minus 4. So we are just going to write it as negative 0.000121. We will just write it that way. That is an approximate value of K. Remember K here, negative 1.21 or no, negative 1.2097. We just make it raised to power 10 raised to power negative 2. So that is what we have here. So we want to solve this equation for T. So that will mean we can take away A0, and we are left with 0.2. Let's write it down. 0.2. We will take away I want to take away this subscript, so I will just write it again. I did not write that equation, so I want to write it now. 0.2. A0 is cancelled, is equal to E raised to power minus 1.2. I'm sorry, let me write it. 0.000121 T. Now solving this equation for T gives us T equals to logarithm of R will be the percentage remaining in general. That's why you have R here. So we have logarithm of 0.2 divided by negative 0.00121, which is 13,301. We rounded it up. So the bone fragment is about 13,301 years old. This is dating using carbon-14. This is the procedure of dating using carbon-14. In general, always use this formula. Always use this formula when you have a problem of dating, knowing that R is the percentage remaining in the material or the object you are studying. This formula is, you don't really need to derive it. Each time you are asked, if you are given the proportion of carbon-14 remaining in an object, to determine how old that object is, just use the formula T equals to logarithm of R, the proportion, divided by negative 0.00121. Using Newton's law of cooling, I just want you to give you the formula here. The temperature of an object T in surrounding air with temperature Ts will behave according to the formula T of t equal to A EKT plus TS. That is, you take an object, maybe from an oven, like an egg you just finished making. You know the room temperature, TS. You want to determine what is the temperature after T, where T is time. The formula is given here. So, logistic growth model. In a logistic growth model, we have a kind of rational function here involving exponential. F of x equal to C over 1 plus A e to the minus bx, where C over 1 plus A is the initial value. That is, when x equal to 0, you have C over 1 plus A. In most of your homework and quiz question, you will be asked the initial value of a logistics problem. The logistic problem will be given with f of x equal to C over 1 plus A e to the minus bx. So when x equals to 0, the initial value is C over 1 plus A. So C is the carrying capacity or the limiting value, the maximum value we can have. Sometimes it will be given to you in the problem, or if the logistic growth model function is given to you, you can know that C, when it is expressed in this form, C is the carrying capacity. You can observe that as x tends to infinity, we have f of x is C. B is a constant determined by the rate of growth. Example 6. An influenza epidemic spread through a population rapidly at a rate that depends on two factors. The more people who have the flu, and the more rapidly it spreads. And also the more uninfected people there are, the more rapidly it spreads. These two factors make the logistic model a good one to study the spread of a communicable diseases. And clearly, there is a maximum value of the number of people infected, the entire population. For example, at time t equal to 0, there is one person in a community of 1,000 people who has the flu. So in that community, at most 1,000 people can have the flu. So researchers find that for this particular strain of the flu, just like we are going through a flu pandemic, the coronavirus, so we may know the maximum population, for example, of the United States is 300 million, so that will be our C. This is how we set the logistic growth model. And we know that we are given here that it depends on this constant. The strain of flu has the logistic growth constant, B equals to 0.6030. So researchers have already determined this value of B. So we can use it to fit into the growth model, the logistic growth model. Estimate the number of people in this community who will have had this flu after 10 years. Predict how many people in this community will have had this flu after a long period of time has passed. That is, let's say after infinity. In other words, will this flu kill everybody at a certain time? So here C equals to 1,000, B equals to 0.6030. So what we need to obtain the model is the value of A. To find A, we use the formula that the number of Ks at a time t equals to 0 is 1, for example. So we started with 1. So at t equals to 0, the initial value is C over 1 plus A, which is 1. We solve for A, and we will get A equals to 999. And the equation of this model is f of x equals to 1,000 over 1 plus 999 e to the minus 0.6030x. So after 10 years, f of 10 will be 293.1, which is about 294 people will get the flu after 10 years. So the maximum capacity here is 1,000 because that is the number of people in that population. You will have some question on logistic growth. So remember, initial value, limiting capacity. So this is the graph of this logistic model that we can use.